ask him more about it. Okay. All right. So I hope you're. I mean, I'm not sure. I mean, it seems to me when I read it, it seems like it's probably underwhelming you. But am I right? You're following the material well, right? The book is easy. Stein is pretty easy to follow and clear, and hopefully the notes are what I'm writing here is easy to follow as well, right?
That's underwhelming.
All right, thank you. Because I mean, I was sitting in complex analysis a while ago. You know what is it? What year was it? You know, sitting like this, making a very smart face, understood? No, you know. But my face is very smart, so you know, people don't suspect. All right.
You said we're going to do sequences. What are we going to do after?
After what?
Integration?
Integration is never, ever over. Right? It just doesn't stop, right? No, I mean, we're going to try to go through chapter 8 and maybe get to the Riemann mapping theorem, right? And right now we're trying to finish chapter 3. So this is not really mentioned as much in Stein, but let's nonetheless talk about it. Oh, actually, even before I introduce this new topic, I just wanted to just briefly talk about, go back to removable singularities. So we said that if z equal to 8 is isolated singularity, the implication is that f is holomorphic in the punctured disk z minus a bigger than 0 less than r for some r. Right? So it's holomorphic there. And we would say removable if and only if limit as z goes to a of z minus a times f of z is 0. So I just wanted to just make sure that you understand why this can be arrived at very intuitively. Why is that is the condition where it's removable? So you would reason as follows. Intuition. Just very briefly, what's the intuition? If z equal a is removable, then we can say that there is a g of z which is equal to f of z on the disk of radius r centered at a minus a. With g of a equal to limit as z goes to a of g of z, which then means the same as limit where z goes to a of f of z, because g of z and f of z are the same. Agreed? And the implication then is that if it's removable, that f is bounded, because the limit would even exist. F is bounded near a. You agree? So I mean, if you just think about just, okay, suppose I found a removable singularity. Well, the function will be bounded, right? And that's what you would find necessarily. Now, if you have this extension, You can also look at the, I mean, why consider this limit is because, again, you would see that that g of z is just some power series, a0 plus a1 z minus a plus a2 z minus a squared, and onwards. So obviously z minus a times g of z in the limit will be z minus a of f of z which has to be 0. Okay, so you can see that, and then of course the more tricky part, is just to show that this is sufficient. So this is a necessary condition, right? A function, for it to have removable singularity, it's necessary that it will be bounded. It's necessary that this limit be equal 0. Okay, so the necessity is detectable right away, right? And as soon as you detect necessity, you might ask, well, is it sufficient? And if it's sufficient, then that's the more complicated argument with the triangles, with proving that it's sufficient. Okay, but that's how you notice this argument, and that's why you start possibly believing that it has to be true. Really, the reason it doesn't work for real analysis is because a lot of functions don't have power series representation. That's the difference, right? If you had power series representation for a function, then the same thing must be true. All right, so this is now the new topic. So I'm mentioning this because I already have at least one interesting question that goes through a lot of that stuff that is going to be on your second exam. And maybe if you like it, I'll put it on your final, on your comprehensive, right? So the index of a closed curve. Or winding number. Let's just say a few things about it. So if alpha of t is equal to a plus e to the I 2 pi n t, and t is between 0 and 1, then I can say that the integral over gamma of 1 over z minus a dz, by just parameterizing it, it's very easy to see that this would be 2 pi in. So the general question, in general, what would be the integral over gamma of 1 over z minus a dz if gamma is a closed rectifiable curve and a is not on gamma, because we don't want it to explode to infinity there in the middle, right? So that's the general question. So here is a very very basic argument on first glance. We try the following. Argument. So I can take the integral over gamma of 1 over z minus a dz and say that, well, 1 over z minus a, this looks like the derivative of a logarithm. So I can say, well, this would be just the logarithm of z minus a evaluated from gamma at 0 to gamma at 1, right? Which ends up being log gamma 1 minus a minus log gamma of 0 minus a, which, if you know how the logarithm is defined, this can be written as the natural logarithm of the absolute value of alpha of omega 1 minus a divided by omega 0 minus a plus the plus I times argument alpha 1 minus a minus argument alpha 0 minus a. So since we have that alpha 0 is equal to alpha 1, so the integral reduces to I. So the first argument, you see, so argument of gamma 1 minus a, so we were going around the curve some amount of time. So that might be something of the form argument of gamma 0 minus a plus 2 pi n. So in other words, this is the point where I began, and I return to the same point. But as I return to the same point, I go in a circle, so I might be gathering the angle. I might be winding the number, right? And then minus argument 0 minus a which will then be equal to 2 pi n times I. Okay? So the problem with this argument is that argument of any number might not be well defined. In other words, I have argument of alpha 0 minus a. There might not be, to cancel this and that, I might not have a good definition. There is no unique value I assign to this and to that. So they don't necessarily cancel well. So, I mean, so here is how this is done more rigorously. So this argument is essentially what's happening. Essentially why you will expect to always, if you integrate around closed curve, you will expect to see 2 pi n times I. But the problem is that as you go around, if this thing, if this curve goes around 0, then the argument is not well defined. You cannot define it in a full circle around 0, because some point will be, let's say, the argument is 0 or 2 pi, or So proposition if gamma is a closed rectifiable curve, and A is not on gamma, then one over 2 pi I integral over gamma z minus A is an integer. Proof. So we're going to define function g from 0, 1 to c by g of t equal to the integral from 0 to t gamma prime s gamma of s minus a ds. Hence, g of 0 is equal to 0. G of 1 will be the full integral around the curve dz z minus a. And if I take g prime of t, I will get alpha prime of t, gamma prime of t, sorry, over gamma t minus a. Right, so really the way to prove that the derivative of g will be this expression, you see it's not immediately obvious. In calculus, if you investigate that, you can think that the derivative would represent a limit over the average value of this curve. But the same thing will happen in this situation if you draw it out. Right? If you understand in the fundamental theorem of calculus why this would be an antiderivative, when in the case where this gamma function is real, then this argument can be actually generalized in the case this function is complex valued. It's not, notice it's not over z, it's over t. So it's a line integral. Right? If you want to, we can talk about it. Possibly if you want to stay in office, I'll show you. So we have that this derivative will be the inside. So what we're now going to do is we're going to define the function h of t to be equal to gamma of t minus a to the power times e to the power of minus g of t. Now, just how do you come up with such a function first? So if you look at g of t reminds you of what? What is g of t reminding you of? What function? Exactly. It reminds you of the logarithm of gamma, right? So therefore, you expect that if I take e, I mean, I cannot argue, I cannot say logarithm, right? So without saying, because it's a complex value, right? I cannot say logarithm. Gamma is, it has the real part and imaginary part, right? So you have to be really careful that you understand why g prime of t is equal to that. Right, so you need to kind of just investigate that the same argument of fundamental theorem of algebra, fundamental theorem of calculus, will work to show that g prime is this. But your intuition is that this is the logarithm. So if I take e and I take e and raise it to the power of g of t, what will I get? I will get gamma s minus a. So if I take e and raise to the power of minus g of t, I'll get 1 over it. So h of t looks to me like what function? Like if just by doing this intuitive analysis, h of t will be equal to really what? Yeah, those are a lot of words, right? So let's just make a track of it just for a second, right? So g of t looks like logarithm of gamma t minus a. Intuitively, right? That's I can define this integral. This integral is well defined, whereas I cannot be sure that the logarithm is well defined. So doing this from a rigorous standpoint is illegal, right? But you can break the law and you can say, well, that's what's happening, right? That's why, so then if you took the derivative of g of t, you would get what you have in the integral. You would get this times that by chain rule, right? The derivative of logarithm is 1 over, right? So this is g of t. So what I can try to do is I can look at the function e to the g of t. Well, that would look to me like what? That looks to me then like gamma of t minus a. Right? So they look to me like gamma t minus a. And therefore, if I have gamma of t minus a times e to the minus g of t, that will look to me like what? Yeah, which is 1. Brilliant. So this looks to me like 1. So in essence, I define this function h of t, and because I don't have this side here, I'm going to just verify that h of t is equal to 1. Okay? So what we do then is we do the following. Then h prime of t is equal to, take for derivative here first, so it will be gamma of t times e to the minus g of t, and then minus, if I now keep this function here, so it will be minus gamma of t minus a times e to the minus g of t times the derivative of g prime of t, which will be gamma prime of t divided by gamma of t minus a. Right? So once you simplify this, you observe that what you get is gamma prime of t e to the minus g of t minus gamma prime of t e to the minus g of t, which is equal to 0. Yep. It's equal to 0. So what's the implication? The implication is that h of t is constant. Now what's the constant? So I can first evaluate what is h of 0. So h of 0 will have to equal to h of 1 in particular, right? H of 0 will be gamma of 0 minus a e to the minus g of 0, which is simply gamma of 0 minus a e to the g of 0 is e to the 0, right? So it's just this. Now this is supposed to also be equal to h of 1 because the function is constant. Now what's h of 1? H of 1 is gamma of 1 minus a times e to the minus g of 1. And g of 1 is, we mentioned here, it's the entire integral, right? So what do we get? We see that we see from there that e to the minus g of 1 is then equal to, if you don't mind, I'll just write e to the g of 1, right? So e to the g of 1 will be equal to gamma 1 minus a divided by gamma 0 minus a. And since gamma 1 and gamma 0 is the same point, we get that the answer is 1. So e to the g of 1 is equal to 1. Right? So the implication is that g of 1 is equal to what? So e to some power is equal to 1. We know how e is, right? So that has to be 2 pi I n. Okay? And in other words, what we have concluded without using the word logarithm, right? Without saying logarithm, because it's kind of really annoying. You pretend that it's illegal to say logarithm, right? So without using the word logarithm, we have shown that the integral over gamma of dz over z minus a is equal to 2 pi I n. So it's equal to 2 pi I times an integer. And we have proved the theorem. Okay? So again, the issue is that you want to say logarithm, but you can't because you don't know that logarithm is defined, right? You don't know that there is such an entity. That's the thing. That's pretty much what this argument is saying. So definition. I think Lustal asked a question like this on a qualifying exam, so I don't know, maybe I'll repeat it too. Definition: if gamma is closed rectifiable curve in C, then for any a not belonging to this curve, we are going to define nu of gamma at A to be the number 1 over 2 pi I integral over gamma dz z minus A. And this is called the index of gamma with respect to the point A. And this is also known the winding number. It's the winding number of gamma around A. Okay. So a few observations. So recall that if gamma is a curve, we can define minus gamma by minus gamma of t to be just reverse parameterization gamma of 1 minus t. Right? In other words, we just restarted from the other end. And we can have the following condition if we have gamma and sigma. This is if you started the homotopy theory, you are doing something like that. If gamma and sigma are defined from 0, 1 into C and satisfy that gamma of 1 is sigma of 0. So in other words, where gamma ends, sigma begins. Then we can define the sum of those curves So we define alpha plus sigma at t is defined to be alpha of 2t, to speed it up, and sigma of 2t minus 1 when t is moving after 1/2. Right? So you do stuff like that in homotopy theory. So here is a picture of what's happening. So it's something like, here is so this curve is my gamma. And this point here is gamma 1. And I can continue, let's say, gamma 1 if I want to, can go like this. I don't know. So this is gamma 1. So this would be now sigma. Okay. So I can create complicated curves. Just create one curve, and then create another one, and just add them tail to tail, if they return to the same place, especially, right? So there is this proposition which we just state without proof. It's easy to establish it.
We also call the base point also in this case?
If they're all emanating from this point, you can say that's the base point, right? But since this is a closed curve, you can select the base point somewhere else, I guess, right? So proposition. If gamma and sigma are closed rectifiable curves, having the same initial points, then we have that nu of A, of gamma around A will be the same as minus nu of minus gamma around A. In other words, if I just take the curve and I trace it in the opposite direction, I'll get the negative of the winding number. And that will be true for every A that is not on gamma. The second part is that the winding number is additive. So if I have alpha plus sigma A, that would be the same as, and that's because of the additivity of integrals, right? This is really the additivity of integrals. Integral over the one curve plus integral of the second curve. Okay, so we have that. Actually, we can also define the scalar multiplication by a real number easily, right? You can do that by complex number as well, but complex number, yeah, if they have the same point, the points would be rotated the same place, right? I think. So it looks like this defines a linear map, right? Or a module or something like that, but you can investigate, right? So it's almost a linear. It's a linear map, it seems. And that is for every A naught in the union. So we should also observe that a rectifiable closed curve partitions C minus gamma into open connected components. So here is an example. So you might have something like this. Actually, let me draw something slightly different. Here. So this is, let's say this is gamma, and let's say this is traced like this. So this is gamma, and we can see where we have components. So we have this is component 1. This is component 2. This is component 3. And there is one other component, and that is outside of this curve, component 4. This is unbounded. unbounded component. Okay. Now, just let's see, how many components can you potentially have? Like this is just 4. How many can you have? What's the biggest number of components you can have? No, not finite. You can have infinitely many components. What number of infinity? So, can you have uncountably many components? No. Has to be countable. Why no? Because each component is open, and each open component is joined from others and contains a rational number, or a pair of rational numbers if it's complex plane, right? So the most you can have is countable. Okay. There is one exercise. We'll see if I'll give it to you if you want. If not, the exercise is asking to create a curve such that it has components corresponding to any integer. So the winding number inside of each component corresponds to any integer. So in other words, you have a component corresponding to a winding number of 0. You have a component corresponding to winding number of 1, 2, 3, 4, 5, 6, etc. and in the negative direction. Okay? So all numbers.
But what do you mean by that exactly? You mean that if you take a point inside that?
Yeah, we're going to say more about it. Right now we just have this is the winding number, right? So if you take a point inside here, you integrate around this curve and you get an integer, right? And the integer that you'll get by selecting a point inside here is actually going to be the same regardless of which point you select in the component. We're going to actually see that as a theorem right now.
Is it obvious that it goes once around that? No?
Say it again. I mean, in the picture I drew, you can actually look at it and you can predict what it is. Right? I'm going to show a few drawings where you can predict what it is, but you can create a very complicated curve that you don't know what's how many times it rounds around. It's not always as easy. All right, so we can say the following: since any closed rectifiable curve in C is compact, we have that gamma will belong to some disk of radius r centered at 0 for some r bigger than 0. You agree? It's compact. It can be covered by a big disk. It's bounded. Hence, C minus the disk dr at 0 will be contained in C minus gamma. Which implies there is always one unbounded component. Determined by gamma. And the reason for that is since if I look at C minus the r of 0, what would that be? That is the set Z such that the absolute value of Z is bigger than r. And this is connected. And contains infinity. in the extended plane, right? It contains infinity. You see what we're saying, right? So components, how are they built? They are maximally connected sets. So this is connected. You agree? It's like a ring. It's like an annulus. Yeah, an annulus, right? Or what do you call it? Or a punctured disk out of the plane. So this is a connected space. So in this connected space contains infinity, and it's contained in those components, right? So it has to be it's swallowed by one of the components here. So this C minus gamma, this is the collection of components, right? And this is a connected set that belongs there. So a connected set must belong to one of those components necessarily. Agreed? Because those components are disjoint. 1, 2, 3, they are disjoint, and 4 is disjoint. So it must be contained in one only. Yep.
When you say complex plane minus gamma, you mean all the points interior to?
All the points, well, interior or exterior, whatever you like calling it, but basically all points that are not on gamma, not on the curve, right? So I take a complex plane, I remove that string, that's the curve, right? What I obtain is, just like in this picture, I obtain disjoint connected sets, right? I obtain disjoint connected sets, those are my components. Now, what I just showed here is that because the curve is compact, I can select a very big disk, and outside of that disk, the outside of this disk is going to be contained in C minus gamma. Right? And that means what? That means that since this set is connected, it must be contained in one of the components. So that tells you that there is only one component containing infinity, because infinity is brought with this component. Yeah? So that means there is only one unbounded. It seems obvious in those pictures, but I mean, you can just look at monster curves or some crazy curves, and where it's really, really unclear what's the inside, what's the outside, how many regions are possibly big. Yeah, okay. So let's prove a theorem. So that theorem is asserting that over each component, the winding number remains unchanged. Then the winding number around the point A is constant for A belonging to D, which is a component of the set G, which is C minus gamma. Also, nu of gamma at A is equal to 0 if A belongs to the infinity unbounded component. Okay? So the winding number around any point in 4 is 0. Proof. Define f to be a function from G to C by f of A equal to nu gamma A, we show that f is continuous. Since f is integer valued, you agree for any point it will be an integer, we proved that. Since f is integer valued, in other words, if I take the image of G under f, that will be contained in the set of of integers. It follows that f of d must be equal to some integer for any component d of G. Oh, why is that? Because D is connected, which then will imply that f of D is connected and a subset of the integer, which implies it has to be a point. You agree? Z is extremely disconnected, so if I show only that f is continuous, there is no other thing that can happen, right? Because it must map connected sets to connected sets. So all that remains to do is show that it's continuous. So what we're going to do is so let's say this is showing f is continuous. So we will fix A belonging to G, and we let R be equal to the distance of A to gamma. So the picture is here is gamma, and here is A. So the distance is just somewhere over here is the distance is R. Smallest distance, right? So this is R. So we have a ball of radius R completely protected against the curve. The curve does not penetrate this ball. So what we're going to do is if A minus B is less than some number delta, which is itself less than 1/2 R. So in other words, where is B? So I'm gonna select a disk of radius 1/2. And B is allowed to be chosen inside of this disk. Okay. So if A minus B is less than delta, then we have that f of a minus f of b, this is equal to 1 over 2 pi absolute value, the integral over gamma of 1 over z minus a minus 1 over z minus b. Easy. My goal is to show that they are the same, right? So if I select any b in here, then those two integrals are the same. Actually, not the same. I don't need to do that. Only that as I take limit as b goes to a, that what I will get is I'll get f of a, or I'll get that this was 0. So this is equal to 1 over 2 pi absolute value integral gamma of a minus b over z minus a z minus b dz. Which is less than or equal to absolute value a minus b over 2 pi integral over gamma dz absolute value of z minus a absolute value of z minus b. So what's your biggest estimate for z minus a? So z minus a is at worst r, right? So I can say this is a minus b over 2 pi integral over gamma. So z minus a is bigger than r. So 1 over r is an upper bound. What about z minus b? Here is a picture. So z minus b, how close can z get to b? Yes, r minus 1/2 r, which is 1/2 r, right? So by looking at this picture, you know that z minus b is 1/2 r at worst. And we have here dz. And what we end up having is this will be, I factor all those things. I factor the r, I factor it all and simplify. So I get a minus b divided by 2 pi actually, if I simplify, it would be just a minus b divided by pi r squared. You see, I just factor all those constants, simplify, right? And I get a minus b pi r squared times the integral over gamma of dz, which is a minus b over pi r squared. And here we have length of gamma. It's rectifiable, so it has a length. Right? So what's the implication? So hence, if I take limit as b goes to a of f of a minus f of b, this is less than or equal to limit where b goes to a of a minus b over pi r squared length gamma, and that is 0. Right? You agree that if B is approaching A, B will have to enter the red circle and eventually be in the blue circle. Right? So therefore, R is then can be assumed to be fixed because R is determined. Basically, I don't consider the limit, and I'm just pushing B until it enters this circle. Continuity is local. So now you see that because length is finite and pi r squared, r whatever small number it is, this is finite, so this is crushed to 0. And the implication is then that limit as B goes to A of f of B must be f of A. Okay, so what we have shown is that we established continuity. So f is continuous at A. And A was arbitrary, right? We pick any A when we show that it's continuous at each point, therefore it's continuous over G. And if it's continuous over G, it would map components to points. So now if you want to just, you can start thinking about this question. I'm not sure if I want to assign it or not. Just question is, can you create a curve gamma for which the winding number, it has obviously countably many components, and basically every integer is represented, right? So basically there is a component for which the winding number is 5, 6, 7, 8, whatever, right? Any number. It has to include all of Z.
Oh, you said all of Z, like every number has curves. Right?
Yeah, 0, 1, 2, 3, and -1, -2, etc. If you can construct a curve, the curve has to be rectifiable. It has to have finite length. Understand, right? So you have to construct a curve that has finite length and such that you have countably many components, and each component represents an integer, or an integer represents a component. So there is a component in which the winding number is 1, in which it's 2, in which it's 3, in which it's 4, etc.
You said basically you're going to have countable, but are we going to have infinite components?
Infinitely components, yes, of course, because otherwise how can you have it? To have all the integers, you must have infinitely many components.
Can we have it still with the rectifiable curve?
It has to be rectifiable, yes. So you just play with simple curves that you know that they are rectifiable. So let's say squares or rectangles or circles, things that you know how to rectify. All right. So curves whose lengths you know, right? So you just take pieces that are curves whose lengths you know and just add those pieces together. That's how you might consider doing it. So this theorem is almost established. We just need to do one more thing. Now, let the infinity be a subset of G, be the unbounded. So be the unbounded component of gamma. Since we already know that f of the infinity will be some integer, pick, you can do something like that, pick a sub r belonging in the set Z such that, so I should say maybe before that, so let's do it like that. Let u sub r equal to Z such that Z is bigger than R, be contained in the unbounded region. Right? So in other words, outside of it, you don't see any curve. Right? The curve is contained in the inner disk. pick a sub r belonging to the set Z such that absolute value of Z is bigger than 2r. Okay? So in terms of pictures, here's what happens. So we have this this disk. This is of disk of radius r, and what my curve is contained in this disk. So my curve is something. Here's my gamma. Okay, gamma is confined to that disk. Now I move an extra distance r. This is also r. And I have this circle. Okay, so I basically had smaller circle and a bigger one, and I just pick any point AR. That's what I'm saying. Pick it outside of this bigger disk. So then, absolute value of f of a sub r will be less than or equal to 1 over 2 pi integral over gamma dz z minus a in absolute value, which is less than or equal to what? So this is going to be less than or equal to 1 over 2 pi z minus a. Z minus a, z is some point on this red curve, right? How close can it get to AR? What's the worst it can get to? R. R. It cannot get closer than R, right? Because this red curve is at worst, it's getting close to this black dot. So we know that z minus a is R, right? So what I have is 1 over 2 pi times 1 over R times the length of gamma. And what you can say is that clearly if R is large enough, we would have that f a sub r is going to be less than some number epsilon, which is less than 1. But if this is less than epsilon, which is less than 1, this number is an integer. It has to be 0. Which implies that f a r is equal to 0, which implies that f of d infinity must be the same as the winding number of f around f of omega around AR, which is 0. Agreed? So I'm not sure. I mean, but basically, a question like that, I know Lustav likes them. Maybe I'm not sure what I have to put there, but here is an example of a question that that I might ask on the exam. Prove that the winding number is 0 in the unbounded component, something like that. Right? And then you just kind of, you see the way you do it, forget about all this argument, forget about that, draw this curve, draw a circle around it, draw a bigger circle, put a point outside of this, and just see, it's a line. It's very easy from there. Right? And then just describe that stuff. How much time do we have? 5 minutes. All right, so let's just finish the examples with winding numbers. So here is computing the winding number by I, so to speak. So here is the situation. So suppose that we look at a curve. So there is a curve. Here it goes. Right, here it goes. And this region is of this curve. This is D1. That's one unbounded. That's one component, and this is another component. So let's say that I look at this. This is my gamma. So let's say I look at this component, and let me just represent it as nu of D1. In other words, because it's clear, it's always going to be the same. Let's say I know that the number here is N1. So that's what I know. I want to know what's the winding number in D2. So I want to know what's nu of D2, which is N2. What is it in terms of N1? Okay. In terms of this number, how do I get across? So let's say the curve gamma is moving in this way. It's moving in this way. So what I do is I'm going to take a magnifying glass and I'm going to zoom in, let's say here. Here's just to look at the border, and let's zoom in at the border with a magnifying glass. Okay? So if I zoom in on the border with a magnifying glass, what I see is the following picture. That's the image in the magnifying glass. So this is D1, this is D2, and this is gamma. Right? Now, what I can imagine is I can just take this small curve, this small segment of the curve, and I perturb it. So I am going to perturb it. I'm going to continuously deform the curve. So now it's going to be like this. This is gamma t, somewhere in the deformation, right? And finally, so you see, when I do this deformation, what's the winding number here? The same as that for D1. You agree? Because it's connected to it, right? There is no change. It's the same. It remains as I deform for any t. As this circle is closing, it remains the same. So it doesn't change, and it cannot jump because the function is continuous, right? So then what I have is, now I continue doing this. And as I continue doing this, you see this thing popped out, and now I have a circle. Yeah? So this is the point that I was pushing out, right? So there was this point, it was moving like a bullet. Here it was, and here it is, right? So this is, let's call this circle C. Okay? And this is, now this is gamma 1, which is equal to gamma plus the circle C. So what can you say? And this is D1. So let's look at the winding number. So, so the winding number at D1 is equal, do you agree that it remained equal, right? It equals to the winding number, the winding number of d1, let's just make it, let's indicate the curve, not winding number of gamma at d1, which is the number n1, is equal to the winding number of alpha of gamma, plus c around the point A. This is the point A here. Right? Where A belongs to D2. What's the conclusion? The conclusion is that because I can break it apart, this is N1 equal to nu of gamma around A plus nu of the circle C around A. You agree? Now, this is the same as, sorry, I keep you nu of, what is this? Nu of gamma around A is the same as nu of D2, because A is belonging in D2. Plus, what's the winding number of the circle? The circle goes clockwise. So what's the number here? It's easy because the point is centered at inside of the circle, and you go around it. What would be the winding number if you calculate it? -1. So here is what we established. We established that nu1 is equal to nu2 minus 1. If the curve is parameterized as I drew it, we have nu1 is equal to nu2 minus 1. All right, so I should let you go, I guess, right? Although this is kind of, it feels like, because I wanted to give you, here you say I have examples where you draw stuff like that, right? Nice pictures. All right, maybe next time